Welcome, rookie detectives, to another high-stakes explainer. I'm your chief detective, and today we're opening a brand new, highly classified folder straight from Unit 6 of our science files. So grab your magnifying glasses and put on your thinking caps, because we are investigating the invisible force that literally changes the shape of the world around us. We're officially taking on the case of the hidden heat. Are you ready to crack the case? I can't hear you. Let's get to work.
All right, here is our top secret case file agenda for today. First up, heat versus temperature. Second, the water cases. Third, expand and contract. Fourth, real-world engineering. And finally, the boss battle mind test. All right, let's open up clue 1, heat versus temperature. You know, a lot of rookie detectives get tricked right at the start. They kind of think heat and temperature are the exact same suspect, but honestly, they're completely different. Here's the absolute crucial point you gotta remember. Heat is an actual form of energy. It's that invisible energy that makes things feel warm. Temperature, on the other hand, well, that's simply the measurement. It's the exact measure of the degree of hotness of a material. So think of heat as the fast-running criminal and temperature as the speedometer we use to measure exactly how fast they're running. Make sense? Now, if we're going to measure exactly how hot or cold a piece of evidence is, we need the right tools and the right language. Detectives all around the world use a standard unit of measurement. We measure temperature in degrees Celsius. So whenever you're writing down evidence in your lab notebook, you absolutely must use that little circle and the capital C. That stands for degrees Celsius. And to measure that temperature, you're going to need our most important detective gadget, which is the thermometer. Inside the thermometer, there's a special liquid that reacts to heat. But here's the catch. If you don't read it perfectly, your clues will be totally wrong. So here are the 3 golden rules of the lab. Rule number 1, you must hold the thermometer perfectly vertically, just straight up and down. Rule number 2, ensure the thermometer bulb at the very bottom does not touch the bottom or the sides of the beaker. If it touches the glass, well, you're just measuring the temperature of the glass, not the liquid inside. And rule number 3, shoot an imaginary laser sight from your eyes. Your eyes must be perfectly level with the liquid's meniscus line. That's just the fancy name for that little curved line at the top of the liquid inside the tube. Moving right along to clue 2, the water cases.
Excellent work so far, rookies. Now that you know how to read your gadgets, let's see how this builds into our next investigation phase. Water acts in very specific ways when it meets our main suspect, heat. Let's look at the timeline here. We start at the absolute coldest point, which is maximum heat loss. When water loses maximum heat, it hits its freezing point at exactly 0 degrees Celsius. It turns to solid ice. But let's say we just leave that ice out on a table. It's going to slowly gain heat from the surrounding environment until its temperature rises and stabilizes at room temperature, which is generally around 27 to 30 degrees Celsius. Okay, but what if we put it on a stove and add a massive heat source? Well, the water temperature rises as it gains heat until it starts boiling away. And that boiling point of water is always exactly 100 degrees Celsius. Now let's crack open clue 3, expand and contract. You're doing great, detectives. Now it's time to investigate the science of shape-shifting materials. Yeah, things actually change their size when heat is involved. When materials gain heat energy, they expand. This means their volume actually increases. They literally take up way more space. It's like they're stretching out. But wait, what happens when we take that heat away? When materials lose heat, they contract. Their volume decreases and they shrink right back down. So just remember this rule. Gaining heat equals expanding, and losing heat equals contracting.
Let's look at the lab evidence across all 3 states of matter: solids, liquids, and gases. In the textbook files, we have 3 famous cases. For solids, we have the metal ball and ring experiment. At room temperature, the metal ball easily passes right through the metal ring. But when we heat the ball up, it gains heat, its volume increases, and suddenly it's too big. It physically cannot fit through the ring anymore. Pretty wild, right? For liquids, we put a glass flask to hold the bottle in ice. The gas inside lost heat, its volume decreased, and the balloon just shrank and deflated. The evidence here is absolutely undeniable. Which brings us to clue 4, real-world engineering. You know, detectives, we don't just solve mysteries in the lab. We take our magnifying glasses straight to the streets. Understanding how heat makes things expand and contract is exactly how scientists and engineers stop real-world disasters. Let's head out into the city for a second. Have you ever noticed the small gaps purposely left between railway tracks? They aren't mistakes. Engineers leave those gaps so that on scorching hot days, when the metal tracks gain heat and expand, they have enough room to grow. Next, look up at the electric cables between power poles. Notice how they're always hung loosely, kind of sagging down? Why is that? Because on freezing cold nights, the wires lose heat and contract. If they were pulled super tight, shrinking would cause them to snap right in half. And finally, the next time you buy a bottle of your favorite drink from the store, look closely at the top. Commercial bottles are never filled all the way to the brim. They intentionally leave an empty space at the top so that if the liquid gets hot during transport, it has room to expand without completely bursting the bottle open. That's just brilliant engineering, right?
And now it is time for the Boss Battle Mind Test.
Okay, rookies, this is round 1. You've gathered all the clues and you've reviewed the case files. Now it's time for the ultimate trivia showdown to see if you have what it takes to be a master detective. Think all the way back to the very first clue we uncovered today. I need a true or false answer from you. Are heat and temperature the exact same thing? Go ahead and shout your answer out at the screen. If you said false, you nailed it. Heat is the actual energy that flows into an object, while temperature is the number on our thermometer, measured in degrees Celsius, that tells us exactly how hot or cold it is. Huge congratulations if you got that one right. Moving right along to round 2, where we play Spot the Mistake. Imagine another detective is in the lab. They're standing tall, looking way down at a beaker on the table, trying to read the thermometer from a really high angle. What is this detective doing completely wrong? That is a massive mistake. If you read the thermometer from a high angle, your reading will be completely inaccurate. You must crouch down and use your laser sight. Your eyes must be perfectly level with the liquid's meniscus line to get the true temperature. Never ever forget the 3 golden rules.
All right, it all comes down to the final round. This is a high-stakes scenario, detectives. Imagine you are the engineer building a brand new train line, but you completely forget the science of Unit 6 and you build the metal railway tracks tightly packed together with absolutely 0 gaps between them. It happens to be the hottest day of the summer. So, what is gonna happen?
It would be a total disaster because the metal tracks gain heat from the blazing sun, they expand. And because you didn't leave any gaps, they literally have nowhere to go. So they push against each other and buckle, bending completely out of shape and ruining the railway. Great job today, detectives. You have successfully mastered the mysteries of heat, temperature, and shape-shifting materials. But before I close this case file, I really want you to think about this one thing. If heat is an invisible energy capable of changing the size of solid metal, what other invisible forces are secretly shaping the world right under your nose? Keep your magnifying glasses polished, keep asking those big questions, and I'll catch you on the next explainer.